administration, il me fait plaisir d'être parmi vous. Donc, si vous permettez, je vais faire la présentation en anglais, d'accord? Mais les questions, on va les prendre en français, d'accord? Donc, c'est juste pour montrer plus cohérent. Donc, so I will tell you a little bit about challenges and innovations in yes, tell me.
English or French is fine, but a little bit more volume.
Louder. Louder, okay. Yes, so about challenges and innovations in corrosion modeling. Okay. So let me start actually with the problem. So, I mean, the problem with, of course, we all like renewable energies, but we cannot deny that we also rely on oil and gas. And so the oil and gas production plants, I mean, suffer from potential catastrophic materials degradation. So these phenomena actually affect the process equipment and also that are applied in natural gas conversion at elevated temperature and pressure, and also they lead to the disintegration of metals and alloys into, in the case of metal dusting, for example, into dust of graphite and metal particles. So if you see here, for example, so you see that syngas itself actually is composed of carbon monoxide, hydrogen, water, and carbon dioxide. And then in this case, you see that there are risks actually of metal dusting that I will explain to you, okay? One, actually, we are in the regime where the reduction potential and oxidation potential of this species actually are competing with each other. This applies to carbon monoxide steel reforming, hydrogen plants, methane reforming, and so on and so forth. So I'm referring to this, so I mean, only in the early, I would say, 2010 and so on, that we started to have enough computational power and tools to be able actually to look into corrosion phenomena from atomistic point of view until, of course, a large scale or using finite element calculation. And in this case, so I just put this very nice special issue here, actually, that is still tiny. But what I want to emphasize is that, for example, if we take this problem, which is called metal dusting, okay? So this is a problem that was brought to us by industry, okay? So from, we worked with Shell, I mean, the Research and Development Center in Qatar, and also Shell in the Netherlands. So what happens is that when they operate their equipment at temperature around 550 Celsius and also at low pressure, they actually notice that there is decomposition of carbon-containing molecules to form carbon on the inner surface of the equipment. And what happens is that you see that, you know, this is the reaction is happening on the surface. And then you see that there is the formation of the so-called cementite, okay? And the growth of cementite. And also what you can see here that, so there are some iron nanoparticles that are on the top of filamentous carbon that are like participating to further catalytic reactions on the surface. So you see what kind of damage actually can happen in this case. Now, if we look at the main question, so this was a very well-known problem, but the main question that industry had is that what what they do is that in order to mitigate that, they introduce like very small concentrations of H2S. Okay? So ppm concentration, which is particles per million. And you see that in this case, actually, in terms of corrosion for the testing rate, okay, decreases as they increase actually the amount of H2S they introduce. It's common practice, okay? They need actually to really balance it to avoid other phenomena. But I mean, they wanted to know what is governing it from the atomistic point of view and how it is actually happening. And sometimes, I mean, how could we find the optimal H2S concentration depending on the gas mixture? Another problem, so this was like a topic we worked on for 2 subsequent projects, and this was done with the Hamad. Then we had a 3rd project with Shell. At this time, so they had another problem. So the problem was happening at temperatures that are much lower, between 150 Celsius and 250 Celsius, but at high pressure. And what they have noticed that dry syngas corrodes the carbon steel. So you, as you know, in large petrochemical plants, we cannot use stainless steel, it's too costly. So we use carbon steel. And in this case, what happens is that the reaction of iron and carbon monoxide led to the formation of this gas, which is iron pentacarbonate. So what happens is that they have noticed that they have iron loss, okay, thinning of the pipe, release of iron pentacarbonate, even if it was like few millimeters per year. But what was actually nasty is that their catalyst was poisoned by the gas. They had catalyst poisoning, which means that the catalyst was deactivated because of the gas. So, and then they shared with us the following figure. So you see here, for example, so this is the corrosion rate. So you see it's very, very small. It's in millimeters per year. It's really nothing. But then as function of temperature, and then they have like compared their graphs actually and the field data in with the literature. And this is all what we had. Okay? So they said, okay, can you actually help us to understand what is going on? Something else that they had also, they couldn't understand, that they couldn't actually comprehend, is that, I mean, when they injected H2S, okay, to the gas mixture, or, I mean, they had also water and CO2 and so on, they've noticed in this case an acceleration of this metal-lasting corrosion, which is the opposite, of the carbonate corrosion, which is the opposite of what they would expect, and also the opposite of what we see in metal-lasting. Again, we are talking about even smaller concentrations, which are particles per billion. Okay, so these are the two main challenges that I will tell you about. And so just to say, I mean, you might have noticed that, you know, when we looked at the microstructure and so on, so that there are actually phenomena that are happening really at the atomic level, okay? So at lattice structure. And then it involves also lattice defects, texture, and also the surface roughness, the cracks, and so on. So it's very complex and how to say, a complicated problem actually to study. But then, I mean, now actually with the progress, I mean, the community has made in developing like computational methods, and also the power of use of supercomputers. So, I mean, companies like Shell and so on now have entire divisions actually for computational modeling of this phenomena, and we work with them as well on certain problems. So you see that, I mean, they realize that employing predictive tools for early stages of corrosion initiation is a very efficient cash saver. Okay, so it will prevent them the downtime of the equipment and so on. And then, so they wanted actually, and also us, to understand the initiation of carbonization. So where does it start? Where the first carbons forms, and what is the structure and the composition of this initiation? And actually to develop computational procedures that are informative to enable reducing the testing from months to years. So here, actually, the purpose is really to try to see if we could propose some routes to control the alloy composition, grain size, pre-treatment, and corrosion elimination. It's a very big, like, scope, and you see that it goes into different domains that are related to environment, to the near surface, the protective film, the surface, and then the bulk metal. And each of these environments need to be treated carefully and with sometimes different techniques and computational. Okay, so just to describe, so through, I mean, from 2014 to 2024, so we had the chance to team up with many groups actually over the world. Normand was in Montreal, and also Laurent from Université, Charlotte from Chimie de Lille, and also Texas A&M, Dublin, University of Toronto, and so on and so on. So we teamed up, okay, in such a way so we work and we try to come up with a multi-scale modeling scheme to be able to look into corrosion phenomena. You might, I mean, guess that each of these methods here, for example, so when we are using ab initio methods, and the first presentation highlighted it very well, is that we are limited with the system size, and we are also limited with the time that we can simulate, because every force calculation is very, very expensive. Then we go to semi-empirical, where, I mean, we have seen the case where like interatomic potentials can be used or can be fine-tuned, okay? And then you can reach like larger systems, thousands, few thousands, and then you can reach up to the microsecond. But if you want actually larger samples and then longer time scales, in this case, I mean, you would need finite element methods to be used. Okay. So in this case, I mean, I'm just showing you the scheme for how, I mean, in this multi-scale modeling, so how the interaction between the different work packages was planned to happen, and it happened actually. But I mean, what I would like to do for today is really to focus mainly on the basic functional theory calculations, okay? How we are pushing the limits, okay? And how actually we are using this data to, of course, have better understanding and scale our understanding. These are just the computational details. So just to give you an idea. So if we want to, if you remember, so when we were talking for the first case of the carbon decomposition on the iron surface, so we face a challenge that many people in DRT calculations face when they are dealing with surfaces. So what happens is that when you build your slab, you make sure that your slab has sufficient thickness to be able to converge, okay? So the main properties, including the magnetic properties. And then, I mean, if you are dealing with vacancies or like you want to look at the effect of defects on carbon adsorption, in this case, you will have to conduct some studies to look at the effect of the finite size on that. So you will see here, for example, so you see that, for example, if I take a 2x2, and I will show you what it means, 2x2 iron slab, okay, and 3x3 and 4x4 and so on and so forth. So you will see that the vacancy formation energy is really affected by that. And then that the CPU time is also like going, I mean, really increasing tremendously in this case. So you need to find a compromise, which is this case 4x4 supercell is the reasonable trade-off in this case. And we are dealing with ab initio slab, which has 112 atoms. This is the K-point mesh that we use. And yes, and we're using GGA, PVD GGA. So this is just to give you an idea how the slab thickness. Maybe you have seen in other papers, smaller slabs, thickness, and so on. But we have found that, I mean, there are convergence problems if we use slabs that are thinner than this one. Okay, and this is just to give you an idea about the surface area of these slabs. So this is the first challenge, when you want, of course, to account for defects. And then what I want to show here is that you'll see, for example, if I take the 2x2 slab and I try to calculate the nudge-elastic, so we use the nudge-elastic band method actually to calculate the barrier at the entire the diffusion pathway for the CO, the decomposition. And then you see here that, I mean, we have a barrier of 1.6, and then that barrier actually reduces up to 0.76 electron volts if we go for 4x4. So you see, it's almost doubles just because the CO molecules actually interact with each other, or the molecule actually interacts with its image due to the finite size effect. And you see that actually what made us believe that there was something wrong is that the barrier that we were finding was really too high to explain any decomposition happening at 550 Celsius, right? So this is why we had to increase, and hence we ended up with this barrier. What is interesting is that contrary to this scenario, so the previous talk was also explaining that, is that you start from a situation where CO is tilting and bending. After that, it decomposes, okay, and it goes to the state or to minimum, which is much more stable than the initial minimum, which explains actually that, I mean, you will have these stable carbide formations at the end. So you see that if you engage into DRT calculations, there are so many things that you need to take into consideration actually to be able to get sensible results, okay? And then having some hints from experiments helps you enormously. Okay? So, and this is, in this case, so in the vicinity of a vacancy, we had no choice then to consider the 4x4 because this is already like too small for having a vacancy and the CO, which is nearby. And then in this case, you see that the landscape really has changed. So we have multiple barriers. Okay, so the pathway from A, B to C, and then C, D to E, and so on. But you see that what happens is that the barrier in the presence of the vacancy is smaller. But what is also very important is that we have, in addition, a diffusion of carbon to the subsurface. Okay, so we start to see the ingress of carbon into the surface, okay, or to the subsurface. So this is just to give you an idea of the energy landscape that we, I mean, not the energy landscape, but this is the diffusion pathway that we could find in using DLT calculations, okay, for two different scenarios, in the presence of vacancy and without the presence of the vacancy. Now, ideally, okay, we would like to look at the effect of multiple vacancies, right? A groove, right? I mean, in reality, I mean, we don't only, especially on surfaces, so a groove, and so on and so forth. And this actually challenges us a lot. It's really very expensive to run larger surface area calculations. So what we have done, so we were lucky enough to find at the time recently reparameterized reactive force field, that's actually we used to compare it. So what we have done, I mean, this was done with the collaboration with Noma and Charlotte, is that we took the DLT calculations and then we recomputed the diffusion pathway using the reactive force field. And then we can see that in the case of the clean surface, it has actually very reasonable, reproduces very reasonably the DFT results. And in the case of the vacancy, it was not that bad as well. So there was a difference actually in terms of the initial energy in this case. So what we have done with this is that we said, okay, in this case, maybe, okay, if we run molecular dynamic simulations, we should be able to get to capture actually the main phenomena that are happening. So what we have done, so we looked at the reaction coordinates. So this was for the presence of one CO molecule, but in reality, we know that, I mean, the surface is covered with several CO molecules, right? It's very unlikely that the surface has few molecules on the surface. So including 4 CO molecules in this case. So taking that forward, so we have been able to run molecular dynamic simulations using labs. And then we have, had the chance also to control the operating conditions. So in this case, we could explicitly take into consideration the mixture, the C-gas mixture, which is carbon monoxide, water, hydrogen, and also CO2 in this entire simulation. Also, I mean, using this technique, I mean, we could simulate the impact of the sigma 3 and sigma 5 grain boundaries that are emerging at the surface, okay, for a sample of 5,000 atom model. And also, I mean, we have been able to look and to characterize and also fully understand the carbon, oxygen, and hydrogen interaction at the surface. And you see that these are the main actually reactions that were taken into consideration. So just to give you an idea, so in this case, you will see that, I mean, what we are capable when we have good potential, okay? So this is over a time of 10 picoseconds, 20 picoseconds, and 300 picoseconds. And you'll see the evolution actually of the group here, okay? So here we have a sigma 3 grain boundary, which is emerging at the surface, in addition to a group, okay? That would be eventually actually the source of the initiation of the mechanism. And here, for example, when you have the group, I mean, you see that in this case, I mean, you have the enhancement of the number of CO2 molecules that are dissociated. And this can be understood from the point of view of you have more catalytic sites that are accessible, okay, where CO like dissociation is happening. So this is just to give you an idea. So we were very lucky. We did some other work with normal using kinetic art, but this reactive force field, as I mentioned to you, was too actually unstable. Okay, so as soon as we, for example, with molecular dynamic simulations, we are using time steps of 0.5. Yes, very small time steps. But if we are using it in the activation relaxation technique, I mean, we have a lot of how to say, inconsistencies and also fluctuations in the forces and energies. So this reactive force field did not work for us for kinetic art. However, we use the modified EM potential to look only at the carbon diffusion and carbon cluster diffusion in iron. So we looked at it from the surface and also to the bottom. But I'm not talking about it today, okay? Because today I want maybe to focus on how we are leveraging and the power of DLT calculations. What are the challenges? How we can turn them into opportunities. So this is just to give you an idea what you can do, okay, with if you have this this kind of potential. So we looked at 4 vacancies that are separated, and also that when they aggregate, in this case, when you have different grain boundaries that are emerging at the surface, I think what would be actually the dissociation or the number of molecules that can be dissociated and so on and so forth. Okay, now we come to the challenge or the question from the industry that was about what is the effect of H2S. Okay, so now we made sure that we are capturing the main dusting phenomena pretty okay. Now, when we come to H2S, H2S is a little bit larger than the CO2, okay? And it has actually, the orientation of the molecule matters a lot. So which means that we face the following challenge is that in terms of absorption energy, it is not that simple, okay, compared to the case of the CO molecule, because actually we have 7 molecular orientation and we have 4 symmetric sites. So this means that we had actually to use PyMagen, which is a package, and to be able actually to account for the rotations, for the flip, and also for the direction of the molecule, and also the different sites. So this is not the real thickness of the slab. The thickness of the slab is the same as I showed you. This is just for illustration purpose. So what you can see here is at the end, so we found 14 configurations. And then from mapping all different possibilities, we found that H2S actually preferably absorbs on a long bridge, rotated by 45 degrees. Okay? And I mean, we also characterized it. So we looked at all these absorption sites and how they compete and how actually this is affecting the sticking probabilities. This is just to tell you that in some cases in DFT, you might face cases where the molecule is just disintegrating and dissociating. Okay, so it's dissociative absorption, I think. Now, what I want actually to show you is that, I mean, after we found the absorption energies, we started to calculate the diffusions, okay, diffusion values. But then what was really important is that, again, the effect of the slab, the coverage, right? So here when we have 0.25 monolayers of H2S and here when you have 0.025 monolayers. If I'm not mistaken, this is 3 by 3 or 3 by 3 and this is 4 by 4 in this case. So you see that it has an effect, but that H2S actually, the barrier of association barrier is really very low. It's at the order of 0.1 electron. So now how this is affecting the entire picture. So what I showed you is that, I mean, if you have enough computer power, so you can do structural optimization using DFT. You can calculate the energy values using, for example, the energy density band method in VAST or others, okay? If you have the chance as well, I will show you when you are sometimes forced to do that, you can use some ab initio MD. And then, I mean, the main purpose here, if you want to go multi-scale, is to use some other methods. One of them is kinetic Monte Carlo, if you have a good potential. If not, you could use microkinetics and also on lattice kinetic Monte Carlo. Okay. So in both cases, both of these methods, actually you start only from the reaction, the equations of, the equations here for the reactions to be able actually to look at the competition between the different species that are present in the sun. So if you remember when I showed you the first slide, so I told you that this competition between oxidation reduction and of CO and so on, each of the phenomena are at the origin of what is happening there. Okay? So this here, we went even further, okay? But I mean, this is like a work which is not that I cannot disclose yet. It's still under investigation by Shell scientists. So what we have done is that we use also our energetics actually to be able to construct a finite element model actually to look at the pipe corrosion for using a 1D diffusion model.
10 minutes.
10 minutes, okay. Okay. So just here, I mean, going back to the effect of sulfur. So I would like to ask you, so here we are facing the following situation, is that in the experiments, the sulfur concentration were really extremely small. Okay? We're talking about particles of ppm concentrations. You have seen that H2S itself, when it lands on the surface, has different orientations. So imagine how many probabilities and how many configurations we need to account for when we have simultaneously CO and H2S. And probably I will have to make my surface even larger, right? So, I mean, this is a challenge we took, okay? So we started to look at CO co-adsorption, but if you remember, I told you that H2S barrier, it was really small, 0.1 electron volt. So we assumed that, I mean, sulfur will be dissociated on the surface, okay? Will be on the surface, and then hydrogen would have dissolved in the molecular phase. So every CO that comes on the surface and it lands, okay, would feel actually the presence of sulfur. I don't know here what we have done. So we have looked at the absorption energy of CO as function of the distance that's from the sulfur out. And then you can see in this case, okay, so if, for example, the distance from the sulfur atom is really close, so you see that the absorption energy actually is now lowered. Okay, and as you go farther away, but you have to go really very far away from the sulfur atom to be able to reach the place of the clean surface where there are no sulfur atoms on the surface. So this case, I mean, this means that sulfur really has a long range effect. That one sulfur atom actually can affect in a very significant way and over a very long range the probability of CO absorption around it. Okay. So what we have done is that, as I explained to you, so here, I mean, here we are dealing with a very strong concentration of sulfur. If I want to account for ppm concentration, so what we have done is that we use microkinetics, but in this case, so this is the case without sulfur, okay, where we have introduced all the kinetics and all the how to say the reactions that are happening in the system. And this is the case where, I mean, this is with sulfur. But you might notice that sulfur is not among the gases that are, or the species. Is that because we account for it implicitly? Okay? So we do not explicitly like use sulfur, okay, among the species, but we only alter the barrier, okay, and account for the effect of sulfur in this case. So then what you can see, so this is like the most important part of this metal dusting. So you see here, for example, this is what it is. So this is the surface coverage. So this, we are counting, I mean, what are the species that are on the surface. So you see in the regime number 1, so the surface is covered by CO molecules, and these ones are not yet dissociated. So they start to dissociate, and we start to see the emergence of carbon deposition. Okay. We have also oxygen. And we have some CO2 that forms at a later stage. So this is the window where actually of the metal dusting here. Okay, when we introduce sulfur, okay, what we see is that actually we are slowing down. Okay, so this actually the phase where CO decomposition is happening here at around 420, actually it's shifted to approximately 470. And then the decomposition is starting much later, which means that actually the availability of carbon on the surface, or CO on the surface actually is much less, which is due to the effect of sulfur. And this is what we could explain how H2S at the end of the day is retarding the metal dusting corrosion in this case. Okay. Now, very quickly, so the second problem, so which is the opposite, right? So what happens in the opposite case, which is at lower temperature but higher pressure, is that when you flow syngas, which is CO, hydrogen, some water, and so on, I mean, instead of CO sticking on the surface and decomposing, no, you're removing iron and creating this gas. And this is happening. So these are some experimental results. And as I explained to you, we had this challenge to explain why H2S in this case is increasing the carbonyl corrosion, which I mean couldn't be explained from like intuition and from people who are in there. So we had additional challenges because in this case actually we are dealing with a molecular system. Okay, so we have molecular species that are supposed to be forming on the surface, then dissolving in gas phase. Okay, so the DFT calculation that you need to account for. I mean, people who are in the field, they know that. I mean, methods that work well for molecules are too heavy for bulk of surface systems, but like for example PVE and so on, it might not be actually sufficient actually to look to capture actually the properties of these molecules. So the first thing we did is that we looked at some phenomena of this gas phase carbonyl. So this is how this molecule looks like in the gas. So in the center you have the iron atom, and these are the CO molecules. And then this molecule actually undergoes a very pseudo rotation in the gas phase. So it's like flickering between the C4V symmetry and the pH symmetry. So what we wanted to do, we wanted to make sure that the DFT method we use is capable of capturing this gas phase properties. Another challenge, okay, is that, is that actually are not playing. Is that actually the removal of CO molecules in the gas phase as well needed to be taken into consideration, and the subspecies of carbonyl. So FeCO5, 4, 3, and 2, if we are assuming that there is actually sequential addition of CO molecules. You see here the simulation of the desorption of the molecule. So this requires as well even a larger slab, okay, what we considered for sulfur and for CO alone, because the molecule itself is more bulky. And then we had to trade off a little bit and reduce the number of layers that you have these. So just to give you some ideas, so this is how challenging and how the energy landscape would look like, okay? So you see here, for example, we attempted to try to see if we could actually manually remove actually the molecule and so on, so we look at the energetics, because it doesn't make sense to go and try to reconstruct the entire energy landscape if you are not, even if you have not localized your minimal problem. The thing is that what we found, so despite all attempts, we found that the iron pentacarbonyl actually cannot form on clean surface. Okay, so we did each and everything. And here, you have a lot of possibilities and scenarios that you need to consider. And you found that from the energetic point of view, the iron pentacarbonyl cannot form on a clean surface. So we had to pull a little bit of what we have learned from LD simulations, from in the previous project, and we said, in reality, the surface is not. Iron pentacarbonyl will not be alone on the surface. there is a need actually to have several CO molecules absorbed on the surface to be able actually to form it, right? And then the question here is really to find what would be actually the optimal or the maximum coverage, okay, of the surface. So we conducted DFT calculations to look at how the total binding energy actually is correlated with the CO coverage in monolayers here, okay? And we found that with the optimum, okay, between the average CO binding energy and the total binding energy is at 0.66 monolayers, which is approximately 2.3 monolayers. So this means that the most stable configuration would be that the surface would be always covered by up to 2/3 monolayers of CO. So we did that. So we looked again at the energetics. We looked at the absorption energy of each of the species. So what we see a priori is that indeed you see that the absorption energy is really very strong. I mean, for each of the species, if we are dealing with a green surface. If we increase the coverage to 1/3 monolayer, it increases a little bit. But then when we take it to 2/3 monolayers of CO, it has like very good increase. But this still cannot actually explain that we would be able to completely desorb any of these carbonyls actually, even that this binding image. So it was really puzzling and it was like a dead end for us. Luckily, we have enough computer power. So what we did is that we did DFT calculations, ab initio MD, and we let the system evolve. And then what we have noticed this movement here. So if you have noticed, so you see that there was an iron atom that has been removed from the surface, okay, due to the reaction with the CO molecules, and it has hopped actually on top of the CO molecules. You can see that, yeah. And in this case, so the iron atom here is bound already with 3 CO molecules. So actually, what we did is that we said, okay, now maybe there is another phenomenon that we can account for, and we took that configuration and we started from FeCO3 and we started to add, CO molecules, and you see that in terms of absorption energy, so we reached a point where actually adding the next CO molecules led to the desorption of the molecule of the pentacarbonate. So at the end, so just to say that everything actually was also supported by analysis of the charge density differences and to explain what was going on and so on. And at the end, you do all this hard work to get this kind of diagrams. And these are like the 2 possible pathways that we have identified. But this is very relevant operations. So you have different transition states, intermediates, and so on, in such a way, and until at the end, actually you end up with this pentacarbonate desorption that requires the involvement of other CO molecules in the system. Yes. Okay. So 1 minute. So this is just to give you quickly how we tried to solve the enigma of the sulfur. So we did the same procedure as we did in the other project. We took CO molecules, we took sulfur, and we tried actually to look at the absorption energy. And you see that, regardless of what we do, we're seeing very similar trends. So we don't see very trend that is showing that sulfur actually could enhance the carbonate corrosion. So in this case, so we had to go to other methods. So in this case, we used kinetic quantifier. So we scaled up to understand how we could mitigate the carbonate corrosion. So in this case, we used a KMC code called Zacros. Okay, and then the power of this is that you can simulate over a year. Okay, so this is in this case. So you see here, so this is the surface coverage in the by accounting without accounting for sulfur, and here we're accounting for sulfur. So you can see that at the end, if you look at the surface from the top, and these are all the species actually that we have identified. Okay. So what you see here is that in this case, I mean, you have the presence of the different species and carbonites and so on. But in these other cases that you have a lot of dust carbon deposition, okay? You see in yellow, due to the presence of okay? So this is, I mean, lesson learned from the previous project. And this actually implies that if we look at the carbonite corrosion in millimeters per year, and we try to compare it to the experiment, okay? So we see that actually our corrosion rate is orders of magnitude higher, okay? So here we're talking about 1.5 millimeters per year, and it's 10 to the minus 3 millimeters. So there is like disparity in terms, but I mean, in terms of behavior, this is actually the same behavior that we see from like, the Shell GTM. And you can see that in this case, so sulfur actually is reducing the carbonite, sorry, is enhancing the carbonite corrosion. Okay. Finally, I mean, the way we could capture the quantitative or more quantitative value is to account actually for the presence of H2, right? So as I told you at the beginning, syngas is composed of CO and hydrogen competes with CO for the active sites. Okay? So you see that the more complicated and comprehensive is your model, of course, it will give you better results. But at the end of the day, it's a matter of cost and also like tools that you have actually to be able to account for it. So I will finish with my final remarks. Okay, you might, I mean, very simple at the end. So I mean, we were like a multidisciplinary team, and we had even like some colleagues that were trying to train a machine learning potential actually for this particular case, because there was no potential that existed actually that would work well. So they've used the snaps and also Jacobi Legendre. So our role, I mean, as like a team member is the DFT calculations that we did on trajectories. I mean, they needed to be really managed very well in terms of data. So we created this collaboration hub in such a way that so the exchange of data is more smooth. Okay, the DFT trajectory could be used actually by our colleagues. What we have done also, so we have tried to create metadata and so on. So what I want just to highlight that we are still not yet, but if we want actually to have a very successful integrated multi-scale approach, data management and exchange and standardization is very, very important. Okay? We have some success stories, but I mean, I would say this is just the beginning of it. And then, you know, imagine if we extend this with the community, and if the community can contribute with the DFT calculated data, I mean, how we could make our discoveries much faster. Thank you.
Moi, j'en avais peut-être une, j'en avais quelques-unes en fait, mais disons, allons-y pour une. Vous aviez l'énergie d'absorption, qui allait comme presque linéairement en fonction de la distance. Ça me paraît une drôle de fonction, disons, au lieu de l'exponentielle ou quelque chose comme ça. Qu'est-ce qui explique? Puis la longue portée, j'imagine que c'est parce que c'est des forces ioniques. C'est très longue portée. Et qu'est-ce qui explique le comportement de l'air?
En fait, donc, ce qu'on a fait, c'est qu'on a publié ce travail, puis il fallait justifier ça justement. Donc, ce qu'on a fait, c'est qu'on a regardé en fait la distribution de charge sur la surface. Et ce qu'on a remarqué, c'est que le soufre, une fois absorbé sur la surface, n'est pas un donneur en fait de charge. Il deplete the charge. Donc, il prend la charge de la surface, ce qui induit que en fait, l'énergie d'absorption du CO en fait, diminue dans ce cas-là. Parce qu'il y a moins de charge sur la surface. Donc, c'est ce qui explique ça. Donc, ça on l'a fait avec une analyse très similaire à ici, charge density analysis. Voilà. Ce genre de... Donc, si je prends ça c'est pour notre exemple. On voit très bien avec on peut expliquer pas mal de phénomènes en fait en regardant en fait, la distribution de chaque chose à la surface et aussi du point de vue de absorbate.
Merci. Je vois Ludwig en ligne.
Ah oui, bonjour, c'est Ludwig Marquino, département de génie physique Polytechnique. Merci beaucoup pour une très, très belle présentation. So I still have one question. Well, where I come from is we do mostly experiments and we look, for example, at the interaction of crude oil, which of course contains sulfur, and how it would affect corrosion on different surfaces exposed to that at high temperature, high pressures, and industrial environment. So I have a question with respect to the modeling, which of course focuses on the interaction of individual molecules, and you calculate the probabilities of attachment and diffusion. But in principle, you have a competitive process because different molecules arrive at the same time at the surface, and then only some of them would react among themselves or diffuse into the bulk of the material and react. And also, since, of course, which is one of the limitations of the calculations you have shown, is you are limited to a limited number of atoms. So it's difficult to probably distinguish between the real surface property with respect to defects, vacancies, or grain boundaries, and so on. What would be the probability of interaction? Can you comment on it? How far you think the modeling can bring us if, of course, you have all this accumulated knowledge? How long and how far one can go with the modeling to try to simulate or mimic the real-life experiments?
Thank you very much for this insightful comment. So I would say that the farthest we have been, okay, is as follows. So I didn't show it here, but we have run very large, I would say, like tens of thousands of atoms, okay, of iron. And in the case of metal dusting corrosion, okay, where actually we have been able to, I didn't mention it, but there was also the question coming, what is the effect of the steam? What is the effect of water? Okay, so we were lucky enough to be able to have interatomic potential that was working very well, okay, for the surface reaction. But as you have mentioned, if you're accounting for like diffusion into the bulk, okay, there was, I mean, the same potential was not working. It was just working for the surface reaction. So we had actually to innovate, and then we had to couple several interatomic potentials together. So we had 3 levels. Okay, I just want to mention. So one for the surface reaction, another one taking care of the subsurface, and a third one which is dealing with the bulk. Okay? And then I've shown you that we have been able to look at the groove, for example, but in the case of water, so what happens is that we have been able to see the interdiffusion of different species to the inside of the sample and so on and so forth. I would say the limitation that we have for H2S is that we do not have a potential to be able to do that. But if we had it, we could apply to a very similar approach. And as a team, we tried to fit our own reactive force field and so on. It's not an easy business. It's a very, I mean, even though when we were in contact with the developers and so on, we had enough data, we built a database and so on, but it's not easy because there is always a trade-off between you optimize one property and then another one goes wrong and so on. But using this hybrid method, okay, where you can combine like potentials of the same kind, okay, together to treat different regions. We have been able to do very successfully with water. I will be able to send you our paper, and then we can discuss further whether, I mean, a case of H2S could be looked at, okay, with using different like similarity.
Okay. Okay. Well, thank you very much.
Thank you.
Merci. Est-ce qu'il y avait d'autres questions? Oui, Hamad.
Merci pour la présentation. Le cas idéal, c'est de supprimer la corrosion. Et donc, si on peut approcher le problème à l'envers, est-ce qu'on peut modifier la surface du tube? supprimer ça.
Oui, oui.
Ce
Donc,
serait quoi comme solution?
naturellement, le carbon steel, il y a une forme, il y a une couche d'oxyde qui protège en fait. Mais en fait, ce qui se passe, c'est qu'il doit toujours y avoir une indentation ou un dommage ou une dislocation ou une veine boundary emerging surface qui crée de la vulnérabilité. D'accord? Donc, il y a toute une science, en fait, en termes de coating, de anti-corrosion coating, que les gens appliquent et tout. Le problème, c'est que ces coatings-là, en fait, sont peut-être trop dispendieux si on regarde le volume en fait, des réacteurs. En fait. C'est pour ça qu'on opte pour le carbon steel. D'accord? Et est-ce que, du point de vue industriel, donc, ce qu'ils préfèrent faire, c'est construire avec un alliage pas très cher et essayer de mitiguer. Mais il y a quand même des équipements qui sont très sensibles, qui sont faits d'alliages nickel, cobalt. Même, on a vu que la petite concentration de molybdénum, de tungstène aussi, aide à mitiguer certaines formes. Il n'y a pas juste les traitements surface, mais l'alliage lui-même. C'est très complexe, mais bon, très intéressant aussi.
Merci. Donc, puisque le temps est dépassé, on va peut-être arrêter maintenant. Merci encore, Fadwa, pour